compound interest compared to quarterly. So what? RE was, I think I gave you the formula already. What's that? A minus E over A minus P, right? Over P, which is A over P minus 1. Then I simplified it for you. It should be 1 plus R over N raised to the power of N. This is my N, okay? Then minus 1. Okay. So really, this is a formula that you have. Let me just write it up here. 1 plus R over N raised to the N power and then minus 1. Okay. R is 7%, which is, R is we don't know. Okay. R is 7%. Okay. 7% means 0.07. N is 4. N is 4. You gotta calculate R. 0.07 is equal to 1 plus R over 4 raised to the 4 power minus 1. They give you the effective rate 7%. What is the actual rate that you really invest if you have it compounded 4 times a year, quarterly, and you earn 7 cents more for every dollar? That's what they're trying to ask you. So look in the formula. Okay, everything has a formula. So look in here. So simplify solve R. First of all, add 1 on both sides. I got 1.07 equal to 1 plus R over 4 raised to the 4 exponent. Then I'll take the 4 root of both sides. I got what? The 4 root on both sides. 1.07 4 root is going to be equal to 1 plus R over 4. And this 4 was my 4. Okay. Because 4 root going to help me to take care of that 4 exponent, and then subtract the 1, which is our algebra now. So 4 root of 1.07 minus 1 equal to R over 4. And all you have to do is what? Multiply both sides by 4. 4 times 4 root of 107 minus 1 in parentheses equal to R. Then plug in your calculator. You should have the answer. Okay. Okay. Now, to show you one more type of question that's actually involved in the log and exponential. This is just about exponential, right? I try to look for an exercise. How long? How long does it take for an investment to triple the value if the rate is 6% compounded monthly? So there's another question. How long does it take? So T equal to how much to triple the value? So you have P. Triple becomes 3P, right? To triple the value. Original amount is P. After some time, it's going to be 3 times. Say, I have $1,000. How long does it take me to invest in some kind of investment that triple the amount? So 1,000 becomes 3,000. And the condition is what? How long does it take for an investment to triple in value if invested 6%? R is equal to 6%. Which is 0.06, and compounded monthly. So monthly means N is equal to 12. All right. So I see I have the N equal to 12 compounded monthly. I know for sure I use the compound interest formula. So let me rewrite the formula one more time. AT is equal to P times 1 plus R over N raised to the power of NT. See, the very first thing is what? I have to figure out what formulas I'm going to use. Make sure that we get the right one. Okay? Now, plug in information. The future amount is 3 times the original amount. So 3P, right, is equal to P. 1 plus. The rate is 0.06. Okay? N is 12. And N is 12 times T. The T is I don't know how much. Okay? I can cancel out the P divided by P and both sides. Let me write up here. I got 3 is equal to 1 plus 0.06 over 12 raised to the power of 12t. I can simplify this number. 1 plus 0.06 over 12 is divided by 6 is to some 0.005, I think. Make sure that I got it right. 0.06 divided by 12. Yeah, 0.005. So this number is 3 is equal to 1.005 raised to the power of 12t. You see that your variable t sits on the exponent. So how do you plot the variable on the exponent? Hint, apply the log on both sides. And as usual, I'm going to do ln. So ln of 3 is equal to ln of 1.005 to the 12t. Bring the exponent down. Ln of 3 is equal to 12t times ln of 0.00 or 1.005. You see by y1 because 1 plus right here. This is 0.05 plus 1. You have this. So solve for t, divide both sides by 12 ln of that number. So t is equal to ln of 3 divided by 12 ln of 1.005. You should have the time. Okay, so I've been showing you all type of problem, really all type of problems you may have in this section. It's all coming around what? The rate, the time, and how many times you compound the interest in the future amount. Okay, there's some people may have a little bit confused between among the something called the effective rate, but I explained to you already instead of just giving you the formulas. So hopefully that helped. Okay, so let me start with section 6.7 right now. Let me move on to the next section, 6.8. I'll be showing you more applications. Now it's not money anymore. It's on something else. We have 3 more applications on 6.8. 6.8, okay? The first one in 6.8 is called the exponential model. Exponential model. Okay. Show you the formulas. The new amount is equal to the original amount. They put a little o right here, o for t equal to 0, and not. That's how they call it. The original amount times 1 plus, not 1 plus, I'm sorry, times e to the kt. I'm glad that this formula is exactly like the financial models formulas if the interest is compounded continuously. Recall that's what we have. AT is equal to P times E to the RT. It's exactly the same thing. Exact same thing. And not here to just use different letters. Okay? And not here is the initial amount, whatever it is. We may not talk about money anymore. We talk about some population, some insect, for example. And E is a constant rating, and K now is a rate, T now is a time, okay? So same thing up here. Oh, let me just write that box first. Okay, where N naught is initial amount, okay? K now is a rate, and T now is a time, and of course NT is a future amount. You know that, right? But with for the formula, we kind of extend it into a broader sense of it. K now could be a positive, it could be a negative number. If K is a positive number, means what? The future amount is going to be bigger than the initial amount, means the population is growing. 2 cases. K is positive, population is growth, so growth. Or growing. It's growth. But if K is negative, means what? The population is decreasing. Okay, say, for example, you have hit the jackpot and you win like $10 million and you don't want to go to work, make more money anymore. Every year you spend 10% of it, right? Compound it continuously. Then what? You're losing 10% annually. And the future amount going to be smaller, or some population was losing the size. It's called decaying. Growing. For money, we only talk about what positive R in here, but actually in money you may have negative R too. If we have bad investment, you can lose money. Okay. Now it's different. For money, usually we use unit for time is what? Year, right? Annually, the rate would be year. But for the general formula, just want to make sure that the unit for the rate and unit for the time gonna match up. If the rate is monthly rate, then the time is how many months. Okay, if the rate is like daily rate or what hour rate or minute, then the time unit is gonna be match up with the unit for the rate. Okay, so if hour, then the time will be total hour. If the rate is per minute, then the time will be total minute. If the rate is centuries, how many centuries, then the time will be how many centuries. Okay, so it's the same thing. And let me show you all the formulas, and then I'm gonna talk about some examples later. That was the first formula. The second formula is from Sir Isaac Newton. Let me find a marker. Just open a new box. The formula for heating and cooling. Okay. Number 2. Newton's law of heating or cooling. Okay. So the formula is actually like this. Ut minus big T is equal to U naught minus T raised to the power of K times T. Let me double check, see if I really have it right. Yeah. And here, K is a negative number. You see, it's pretty similar to the previous one, right? Instead of having E right here, I missed an E. I was wrong. Time E to the KT. That's what I missed. No wonder. You see, this is kind of the original amount, right? Time E to the KT. See, original amount E to the KT equal to the new amount. But in terms of heating and cooling, so you may ask, what are we talking about here? Let me explain it to you. You have an object with the initial temperatures U naught, okay? And you put in some environment with the temperature T, and assuming that the temperature of the environment surrounding, like a room or something, never change. And after the time little t right here, Ut will be the new temperature of the object. Say, for example, you go to a room, bring in a hot cup of coffee, the room temperature is 70 Fahrenheit degree, and the cup of coffee is 160 degree, for example. Then after time t, like 5 minutes, 10 minutes, the temperature of the cup of coffee is going to be going down to a lower temperature. And eventually, up to some point, the temperature of the cup of coffee will be equal to the temperature of the room. That's what it is. So let me explain all the terms in here. Big T is the room temperature or surrounding temperature. Surrounding temperature. Okay. K is the rate. Same thing as for the rate for the temperatures going down. Okay, and of course little t is the time. Okay, U naught is the initial temperature. Just change back to the page of homework so I will see the problem. Okay, and Ut is the future temperature of the object. This is the future temperature of the object. In here we say cooling is, of course, the same thing for heating. Say you preheat your oven to 400 Fahrenheit degree, and you put a cold pizza into it, right? So the surrounding now is the inside the oven things, and U naught is your temperature of the pizza, originally the cold pizza. T here is 400 Fahrenheit for the oven, and UT is the new temperature of the pizza when you put it after the time T. Of course, you know what happened to the temperature of pizza. It's getting hotter and hotter. We follow the same formula. This is what it is. Okay, and this is how I usually write it. But I see that in our book, they don't write minus T in here. They add a T in on the other side. So this is what our book writes, which is exactly the same thing. UT is equal to T plus U naught minus T times e to the KT. That's just the book version, exactly the same thing. You see what we do from here to get to there? We add the room temperature, the constant, T, big T on both sides. Okay, you have it. This and that are the same. So this is what the book writes, so make sure that I got it right. That's why I look it up. Okay, and now the third formula. This is the second one. The third formula called logistics model. Okay. So new population is equal to the capacity over 1 plus. Was that use A or B in here? Let me make sure that I use the right term, like the book. Use A plus. A times e to the negative bt. Okay? So this is our concept right here. They don't use K for the rate anymore, use B. So ABC. So I try to match up with our book formula, so when you guys study it's gonna be easier. Even though in my opinion it won't change anything, it's the same thing. Okay. So what are we talking about in here? We're talking about some population, okay? Growing, follow this model. Of course, the little t is still the time. And C here is Newton capacity. And little b is the rate, okay? B is a positive number, means what the population is growing. B is a negative number. Population is decreasing. The negative in front because we put that rate on the bottom in the denominator. So negative on the bottom is make it positive on top. Okay. B is the rate here. That's right. B is positive number. Population is going up. B is a negative number. Population is going down. Okay. And A is just a constant. Okay. So say you have a population with the original population of, I don't know yet, okay, say 200, okay? Let's just make up a number. And that population grow with the rate B, like annual rate, 5%. Then eventually after some time, we're gonna have a new population. Capacity, what does that mean? This is the maximum population that that species is gonna have after the time change. So it means what, up to some point, the newborn rate is going to be equal to the death rate. How many newborn you have, this is the exact same amount of death rate you have, means that the population will not go up anymore. Okay? And I recall from the past, I'm not sure about our book, but when I studied this, then recall the map looks like this. This is capacity. See right there. Population going to be like this. Okay? Yeah, so we start from here, right? T equal to 0. T right here, 0. This is your original amount. And then when time passes by, the population going up, but will never pass the ceiling right here. This is my C, capacity. C, okay? Population keep going, getting closer and closer to capacity. Means that when time passes by, the death rate gonna be pretty much the same as the newborn rate. So population will stay at that point, given the same conditions around for the surrounding environment. Okay, and of course there's another one like this going down. Means what? Population is decreasing. This is what we have. I think of it positively. Okay, those are the three models. All right, so this one you don't see the initial population in here, but you can calculate it. How? You plug in t equal to 0. You have the initial population. Okay, t equal to 0 when we start. C is not the population. C is the maximum capacity, the highest population possible for that species, okay, whatever it is, okay, highest size, the biggest size of the population, okay. You want to calculate the initial value, you have to plug in t equal to 0. So let me show you a couple examples on 6.8. We have 3 models, so I think I'll give you 3 examples. Look. Okay, I just print out from our textbook the exercise page, so I'll just copy one of those in here. Okay. I have, I see, iodine. It's a radioactive thing, 131. Okay, talk about this. It's decaying. Means what? After the time, the amount of that iodine gonna be decreasing, and they give you the formula. At is equal to A naught times e to the negative, was so small, 0.0, I can't see it, 244t. Okay, that's what it has. Where At, of course, you know that this is the initial amount. Okay, of course, this is the future amount. So if decay means what? The future amount going to be smaller than the initial amount. So after, when the time passes by, that initial amount getting smaller and smaller. Okay. Assume that the scientists have a sample of 100 grams. So a sample go to 100 grams. It means what? They give you the initial amount. Is initial amounts of 100 grams. Okay. What is the decay rate of that thing? Decay rate is here. The rate is right here. The rate. Question A. What is the rate? The rate is indicated in the formula already. The rate R is equal to 0.0244, which is 2.44%. And the negative sign means what? This is decaying, it's going down. Okay? Question B. How much iodine 131 is left after 9 days? So they give you T equal to 9. Question B. What is the amount after 9 days? Amount after 9 days equal to how much? So first of all, you have to pay attention. The unit for the time is T. So the rate right here is really the daily rate, I think. Let me double check on a time in T a day, right? So you understand what the rate here, 2.44% is a day. Every day is going to lose 2.44%. Okay, so plug into the formula. I got A after 9 days is initial amount is 100 grams times e to the negative 0.0244 times 9. And of course, we're going to need a calculator for this. Okay, where's my calculator? Plug it in. 100 times e to the negative 0.0244 times 9, close parenthesis. 80.2840. I'll use it for decimal grams. Okay. So you guys see it's decaying. The original amount is 100. And after 9 days, it's down to about 80 grams. Okay. That's the questions. Next one. When will 70 grams of iodine is left? So the question C, they say this. The original amount is 100, and after a time is going down, so after some time we're going to get eventually to 70 grams. So how do we find the time? So 70 is equal to 100 times e to the negative 0.0244 times t. Okay, so they ask for the time. How much time needed? The original formula is right here, right? The future amount is 70 grams. The original amount never changed, 100. And after some time from 100, it's going to be down to 70. We calculate the time. Okay. First of all, simplify the formula. Divide 100 by both sides. So 0.7 is equal to e to the negative 0.0244t. And you see that I got t on the exponent. I'll do ln on both sides. ln of 0.7 is equal to, this one is ln of e to the 0.0244t, and ln helped me to bring the exponent down. This is 0.-02444t times ln of e, and you know what ln of e is equal to 1? Okay, forget a negative. This is 1 already. Okay, so I can solve for t. t